got a problem up here on the board for you to try. So I've kept up here the definition of the directional derivative, and I've added the plug and chug. This is the easiest way to calculate it, which is equivalent to the definition of it right up here. The problem I want you to try is to find the directional derivative of this function of three variables, x times the natural log of yz. At this point, negative 3, 2, 1 half, in the direction of this vector v, 1, 3, 5. Okay, so pause the video, give that a shot, and then tune back in. Welcome back. Okay, so if I'm finding my directional derivative, the first thing I'm going to notice is that that is not a unit vector. I'm going to take care of that right off the bat, because if I procrastinate, I'm afraid I'll forget. So u is going to have to be v hat. Same direction, but I'm going to just normalize it. Now, of course, that's just v scaled by the reciprocal of its magnitude. Okay. Well, v is 1, 3, 5. The magnitude of v would be the square root of 1 squared plus 3 squared plus 5 squared. So that's 1 plus 9 plus 25. That's going to be the square root of 35. So we're going to get 1 over root 35, 3 over root 35, 5 over root 35. That's my u. Okay, excellent. I don't have to call it u. If I want to call it v hat, I can. If I want to call it by any other name that isn't taken, that's okay. I think I'm going to call it u. Okay, excellent. So then I'm going to also need to calculate the gradient and evaluate it at this point. So, the gradient of f is f sub x, f sub y, f sub z. I like to write that out just to remind me that's what I'm doing. Partial with respect to x is just going to be the natural log of yz. Partial with respect to y, let's see, that's going to be x is a constant times the derivative of the log function is going to be the reciprocal, so 1 over yz, times a chain rule. The partial with respect to y of yz is going to be z. Those z's will cancel, and I'm not concerned about canceling that out of the denominator because I know that I'm concerned about it at this point where z is not 0. Okay. All right, and then the partial with respect to z. Again, x is a constant. The reciprocal of the log is 1 over yz, times the partial of yz with respect to z will be y, and the y's will cancel, and again, I know that my y value at the point I care about is not 0. All right, so that's just the natural log of yz. See, that's going to be x over y, x over z. Excellent. Now that's a formula for my gradient. I need to remember to evaluate it at this point. So the gradient of f at p naught is the natural log of 2 times a half is the natural log of 1. That's going to be 0. X over y, that's negative 3 over 2. X over z, that's negative 3 divided by a half is negative 3 times 2 is going to be negative 6. Excellent. So now all I need to do is dot these two vectors. So duf at my point, which was negative 2, 1 half, is, and it's totally fine for me to use u here because that's what I called this. If I had only called this vector v hat, I would write here d sub v hat f. Whatever name I use for the unit vector, I can put here, but it has to be a unit vector. Okay, so that's just going to be 0, negative 3 halves, negative 6, dotted with 1 over root 35, 3 over root 35, 5 over root 35. So, my first terms give me nothing. I'm going to get minus 9 over 2 root 35, and then minus 30 over root 35. Let's just get a common denominator. So that's minus 9 over 2 root 35, minus 60 over 2 root 35. So that's going to be negative 69 over 2 root 35. Excellent. We should be getting a number because we were evaluating this at a point. We weren't looking for a formula for the directional derivative. We were looking for it evaluated at a point.